Welcome to Know All for GCSE. Welcome to the second daily Easter live streams. Let's start off as usual with the sciences. So, what I would like you to do, here is a timetable just for your reference. And today we're going to start on biology, infection and response, because we did the first two topics yesterday. So I'm going to give you an activity now. I want you to spend 10 minutes writing as much as you can about infection and response. I have written some prompts here for you to help you get started, and I'm going to give you 10 minutes starting now. Okay, everyone. So that is now 10 minutes. So hopefully, I don't expect you to have written the entire thing, but as long as you've tried your best in answering as many as you can. So I got up to roughly number 7. However, I can go through the rest with you and also look at what we missed. If you've missed anything, then I would suggest getting a different coloured pen and editing what you've done. So let's go through them now. So we started off by looking at communicable diseases. And communicable disease are pathogens which include viruses, bacteria, protists, and fungi, and they cause infectious diseases. So, just for clarification here, communicable diseases are diseases that cause infectious diseases. So they're things like, and then we would have had to have gone into depth as to what each one is. So viruses are very small, and viruses move into cells and use the biochemistry to attack cells. They lead to cells bursting because what they do is they terrorize a cell, they go into the cell and they replicate inside of the human body cells and therefore destroy cells. So terrorize the cell, replicate inside healthy cells, which causes damage. So viruses become a host. They use host cells to replicate. And the damage of the cells makes the person feel ill. Then we have bacteria. Now, bacteria are small, not as small as viruses, and they multiply very quickly. So bacteria multiply via binary fission, and it's very rapid. And they produce toxins which can damage cells. Now, these toxins also make us feel ill. So it's a damaging part of the cells that make us feel ill. Then we have protists, which, as we just saw, some are parasitic, which means that they use humans and animals as their host. So protists need vectors to transmit, and some are parasitic, and parasitic means that they use humans and animals as their host. And then ways they spread, you could have said through air, through fluids, direct contact, etc. Now we're going to look at viral diseases. In terms of the definition, a pathogen is any microimmune system through infectious diseases. If you seem to be getting a lot of this wrong or have missed a lot out, then I would suggest later on in the day returning to this and doing another one to see how much you can remember from that point on. Okay. In terms of viral diseases then, viruses are particularly dangerous as they can enter all types of cells, and scientists find it difficult to find medicines against them because then it will be damaging the interior of the cell. So, we have measles, HIV, and TMV as our different types of things. So not exactly AIDS, it's HIV, TMV, and then we also looked at measles. So these are the common viruses that you get asked about. So in terms of the symptoms of measles, you have fever, you get red skin and rash, which can lead to other problems such as pneumonia. And it's spread via droplets. And it can be prevented via vaccination. So you just need to know some symptoms, how it's spread, and how it can be prevented. Then there's HIV, which has flu-like symptoms, so that's correct, and attacks the immune system and can lead to AIDS. And it's prevented by using, for example, barrier methods of contraception, such as the condom. And also antiviral drugs, which stop the drugs replicating in. So it doesn't necessarily cure it, but it stops the virus replicating in the body. And finally, we have tobacco mosaic virus, which is for plants, as we said. And what happens is it causes the discoloration of leaves, which can lead to chlorosis and reduce photosynthesis. It's spread, because we didn't talk about how it's spread. It's spread via contact of plants, and the insects also act as vectors. It's being prevented via good hygiene and pest control. Okay, so that's the viruses done. Now we're moving on to the bacteria and bacterial diseases. So we have salmonella and gonorrhea, which are the two ones here. So in terms of salmonella, salmonella produces toxins which damages cells and makes us feel really ill. And what happens is it comes from bacteria that lives in the gut of different animals, and then we then ingest that by humans, by raw meat, raw eggs and stuff like that, and unhygienic conditions. And it can be prevented via spread raw meat, eggs, and it can be prevented via vaccinating poultry against it so that we're less likely to have it. And then gonorrhea is again another STD. Another STD. It causes very thick and yellow discharge and possible pain as well when urinating. It's, as we said, spread through is a sexually transmitted disease and spreads through unprotected sexual contact, and it's prevented by using contraception. Okay, so that's bacteria looked at. Now on to fungal diseases, and for fungal we have rose black spot, and what happens is it's purple or black spots left on rose plants that reduce the area available for photosynthesis, and the spores, in terms of how it's spread, the spores of are spread through rain, so this is a fluid one, and it's being prevented by using fungicides. And finally, protist diseases, which again requires a vector. So we looked at malaria. So malaria uses a mosquito, a female variety of mosquito, as its vector. It asexually reproduces in the mosquito and then sexually reproduces once it gets to the human, I believe. Or it may be the other way around. Yeah. And so, yeah, it does asexually in mosquito, sexually in humans, and furthermore, it's spread through their saliva. It's being prevented using an insecticide, coating insect nets while sleeping, removing stagnant water, and things like that. Now onto the human defense system, which I just said HDS. So there's things like skin acting as a physical barrier, the antimicrobial secretions, which we call sebum. The nose has. We've talked about mucus there, but it also has hair, which waft bacteria away. The trachea and bronchi secrete mucus, and again, cilia. So I clearly seem to have forgotten about cilia and hair. And the stomach with its hydrochloric acid. Now, we talk about the three functions. Just before we go, we need to talk about the three functions of white blood cells. So, white blood cells have three functions. The first is phagocytosis, which is engulfing cells, engulfing pathogens, and once it engulfs the pathogen, it then alerts more pathogens to come that way and dispose of it. Then there's producing antibodies, and the antibodies attach to the antigens. And once they attach to the antigen, because it's complementary, it has to be a complementary to the antigen. And once it binds to it, the pathogens then clump together, and it is then easier for the white blood cells to find them. Finally, we have antitoxins, which bind to toxins. Okay, now we're on to vaccination. So we've discussed the different stages of vaccination. So it's tested on cells, then it's tested on animals, then healthy volunteers, then allocated patients with the disease, and then given to the entire populace. Then we have advantages and disadvantages of the vaccine. So in terms of advantages of a vaccine, it can prevent epidemics, and it can allow herd immunity. And herd immunity is when enough people have taken a vaccination that even the people who haven't taken it are still safe. And that's also important to talk about antibiotics and penicillin. Antibiotics. So antibiotics are drugs that are used only against bacterial diseases. And the reason why they don't work on viruses is because viruses have a host cell which uses your healthy cells, whereas the bacteria undergo binary fission outside of your healthy cells. So the antibiotics can simply go and kill the bacterial pathogens without damaging body cells. Now, painkillers are often associated with this topic. However, painkillers are not antibiotics because they only relieve the symptoms. They do not relieve the illness. Now, mutations can happen in bacteria. And how mutations actually occur is during reproduction of certain bacteria. So during the reproduction, and also it can happen when not finishing the course of antibiotics. Which is very damaging. So development of drugs, we just need to know about aspirin and how aspirin enabled painkillers, and then digitalis came from the plant foxglove, and then there's also microorganisms such as penicillin. So penicillin came from Alexander Fleming, and it came by accident as he noticed a growth on his he noticed a mold on his petri dish that stopped the bacteria growing, and it had clear rings around the mold, which suggested that it was effective against curing things. Then we talk about preclinical testing and testing, and then monoclonal antibodies. So monoclonal antibodies is a big topic in here as well. So monoclonal antibodies are just antibodies identical antibodies that have been produced from the same immune cell. Identical antibodies from the same immune cell. So what that means is it may become clear when looking at the process. So in terms of the process, you first inject the mouse with the pathogen, with the virus, and then the mouse's lymphocytes, which is a type of blood cell, are now stimulated and begin to produce antibodies. Then these antibodies are extracted by the scientists, and they then fuse them with a tumor cell so that it could undergo rapid mitosis and therefore become a monoclonal antibody, which is an identical bodies produced from the same immune cell. So they're all clones of each other. Now, there are some uses of monoclonal antibodies. So if we're talking about uses, they're used in pregnancy tests with the HCG hormone. They're used in diagnosis. It can be used in diagnosis of STDs for the user to come. And it can also be used in laboratories to measure and monitor the level of hormones and chemicals in your antibodies is that they only bind to specific cells. They can be engineered to treat many different diseases, and we can now produce human mouse hybrid cells to reduce the chance of triggering an immune response. However, it's difficult to attach monoclonal antibodies to drugs. They're expensive, and as they were produced by mice, they often trigger an immune response. Finally, just going on to plants. Plant diseases, we looked at a lot of them, but common signs of plant disease, things like stunted growth, so chlorosis, discoloration, areas of decay, malformed stems or leaves, plant has by using a manual, a website, and things like that. So a nitrate deficiency. So nitrate deficiency is needed to make particular proteins, so it causes stunted growth. And a magnesium deficiency is needed for chlorophyll, so therefore it causes chlorosis. Because magnesium is needed to make chlorophyll, and nitrates convert sugars into proteins. Now, defense responses, finally, last thing. So there's different types of defense responses. There's chemical, which is things like having poisonous plants. There's mechanical, which is things like having thorns. And then there's just physical, which is like having bark on the tree. We could also talk about the tough, waxy cuticle. We could talk about mimicry in terms of mechanical to try and trick animals. Okay, but that is the last of this topic. So if you missed anything, feel free to just look at this quick description of infection response. We're now going to move on to the very next topic, which is bioenergetics. This is a much smaller topic, so it will probably take less time. 38 to write as much as you can about this topic. Okay, everyone, that is time. So now we're going to go through just this very short topic, and then hopefully I think we're going to have time for another additional bonus topic for today's session. So let's have a look here. So the first thing was the photosynthesis reaction, and it's just a process of making glucose from light. So it requires carbon dioxide and water to make glucose and oxygen, and they have their own chemical symbol. Now, in terms of rates of photosynthesis, it's affected by just temperature as well. So you've got temperature, light intensity, carbon dioxide concentration, even amount of chlorophyll is a varied answer, because chlorophyll is a pigment in the leaf that converts light energy for food for the plant and is therefore essential. So if the chlorophyll levels are reduced through a magnesium deficiency, for example, then the rate of photosynthesis sadly decreases. Now, there is a required practical, which is for photosynthesis, which I'm going to go through now. So what you do is you fill up a test tube with sodium hydrogen carbonate, a particular volume, whatever. Then you put a piece of pondweed into the test tube. You leave for 5 minutes to acclimatize, and then after every 1 minute beyond that 5 minutes, you want to measure the amount of bubbles that are escaping. Because as we know in the photosynthesis reaction, oxygen is created, so these bubbles are oxygen. So it's depicting the rate of photosynthesis. Then what you're going to do, after you have the table of values, which will be like 1 minute, 2 minutes, 5, and you have the number of bubbles, you're going to do another row in the table, because you're going to do number of bubbles when the light source, because you have a light source, right, is this certain meters away. This is the independent variable. So this could be when it's 5 meters away. This can be when it's 10 meters away. That's obviously massive. Don't do 5 meters away, but that is what it should look like. Now, you often see when we're looking at rates of photosynthesis graphs. So, for example, carbon dioxide concentration, photosynthesis rates, and it'll look something like this. So this graph basically tells you that when there is this is 100 lux and 50 lux. So this graph is informing you that because this is the light intensity here, it's 50 lux. So it's telling you that at a higher light intensity, the rate of photosynthesis is increased. Therefore, it's a limiting factor, because if a limiting factor is something that if its presence is inhibited, then so is the rate of photosynthesis. Uses of glucose from photosynthesis. There's used for respiration, which is quite obvious actually. Can't believe I forgot that. Respiration, converted into soluble starch, produces fats and oils for storage. Nitrates to produce proteins. Respiration, the exothermic reactions. So aerobic respiration is glucose creates carbon dioxide and water. Glucose plus water makes carbon dioxide, and don't forget the water here. Just think, when you're exercising, what are the two things you have? Well, you're breathing out faster and you also sweat. That's carbon dioxide and water. And then in anaerobic respiration for animals, glucose leads to just lactic acid cells, it's called fermentation. And it's glucose creates ethanol and carbon dioxide. Now, responses to exercise, your heart rate increases, your breathing rate increases, and your breath volume increases. Metabolism are all of the reactions summed up in the body. And examples of metabolic reactions are glucose being converted to starch, glycogen and cellulose being joined together, a glycerol molecule and 3 molecules of fatty acids forming a lipid, the reactions in respiration. There are examples of metabolic reactions, and that is this topic done. So we have now from yesterday and today's session of Biology Paper 1. This means that we have enough time so we can go over the next topic of homeostasis and respiration, or at least make a start into that topic. So, I want you to spend up till 5:55 writing as much as you can about homeostasis and response. Since we have time, I'm just going to go over a few parts of homeostasis. So, first of all, homeostasis is the regulation of all internal conditions in the body. And, for example, blood glucose concentration, body temperature. So, there's 3 things that homeostasis controls: blood glucose levels, body temperature, and water levels. These are the 3 things that homeostasis controls: blood glucose levels, body and temperature, and then water levels. Now we then have to know, as it says on the list, about the human nervous system and then the reflex arc. So, the human nervous system is comprised of, we have nerve cells, and which we call neurons, and we have the CNS system, which is comprised of the brain and the spinal cord, And then you have other parts such as receptors, coordination centers, which is the CNS, and effectors. So we're going to put all of this into action now as we describe the reflex arc. So let's look at the reflex arc. Reflexes are actions that are carried out by the nervous system. They're rapid and they're carried out without the conscious brain. So firstly, there's a stimuli, which is a change in the environment that triggers this. It's a key point. It's external. The stimuli is picked up by receptor cells. We then have the receptor cells have to convey their information to the CNS. But how does it do this? It does it through neurons. So there's a relay neuron, the motor neuron, and the sensory neuron. So we first have the relay neuron. So I'll do the neurons in a different color. And the relay neuron takes it to the CNS. And then during the CNS, it's sent through motor neurons. Relay neuron, motor neuron. And then from the CNS then makes a decision. So the brain and spinal cord make a decision. And then it goes to either two ways. So it goes to muscles or glands. And we call both of these things effectors. They carry out the effect. So we have relay neuron, motor neuron, and then sensory neuron. Which takes you to the muscles and glands, which carries out the effect and response, and that leads you to the final destination, which is the response. And that is the reflex arc. That is all of the conditions that the brain goes through. Now, the next thing we need to know is the brain and reaction time. So let's revise the brain and reaction time. So the brain looks something like this. Imagine that's what the brain looks like. So the main part of the brain is called the cerebral cortex. This is responsible for memory, languages, and consciousness. Then we have the cerebellum, which is the second largest. And we have the medulla. And we also have the hypothalamus. So the cerebellum is responsible for things like, just double check this actually. Cerebellum is responsible for movements. So basically muscle coordination. Let me just write that in red so we remember. Movements, muscle coordination. Now the medulla is responsible for the rates, so the breathing rates and the heart rates. And hypothalamus is responsible for the levels, so like the water levels, the blood levels, the temperature levels, and things like that. But you're not necessarily asked about this, you just tend to be asked about the three other sections. So it's also important that when we're looking at brain, we also learn about investigating brain damage. So when we're investigating brain damage, there's three ways you can do it: MRI, electrical stimulation, or perhaps the most obvious one is looking at damaged brain patients. So let's start with the most straightforward one. Looking at damaged patients with damaged brains, it then allows the doctor to review the effects of damage in a particular area, and therefore work out what that function is because it's now missing. Now, MRI scanning, magnetic resonance imaging, is when you are instructed to, and then the MRI scans will show which parts of the brain light up and are active during that part. And then electrical stimulation is when the parts of the brain are stimulated and you generate a response. So they're the three types of investigating brains and stuff like that. And the next topic is reaction time. So we can talk a bit about reaction time. Well, I think it's probably best to go on to the eye now. So let's go on to the eye. Reaction time is a required practical, so I doubt there will be enough time left. So let's just do some revision on the eye. So imagine this is the eye. We have the lens of the pupil. The iris is in front of the pupil. We have these things here. The outer layer is called the sclera. It's a tough outer layer. Then we have the two muscles here. So we have the suspensory ligaments, and we have the ciliary muscles. It's called accommodation, which is what, so these two muscles change the shape of the lens depending on the distance that they're viewing. And this whole idea of changing the lens shape is called accommodation. Now we have the retina here, which is the back of the eye, and the retina is basically the receptor cells of the entire reflex arc for when you're looking at something. And then we have the optic nerve over here. The lens is some invisible thing here. And then so the iris, so the iris is actually the muscle that surrounds the eye, and it's used to limit and maximize light, and when you're looking at light. And the cornea is the invisible layer that is in front of the eye and allows light through and curves light and manipulates light so we can see things. Now, it's important to look at the process of accommodation. So accommodation is like focusing on a near object, focusing on a distant object. So when you're focusing on a near object, the suspensory ligaments loosen, and so the ciliary muscles. Okay, so the CM contracts when focusing on a near one, and the suspensory ligaments loosen, which therefore allows the lens to thicken and more focus. So this refracts light more, and therefore focuses more. And then when you're looking at a distant object, the ciliary muscles relax. And the suspend as the lens thins and therefore refracts less and focuses less. Okay, so that's enough about the eye for now because we're going to move on, but tomorrow we will continue on with this topic. Now it is time for chemistry. Yesterday we went over bonding and structure and the periodic table, and now we are on to quantitative chemistry. So there are 4 topics here. I think 5 minutes will be necessary because there are just few equations here that you'll need to know. So I'm going to give you up until 6:05 to write as much as you can remember regarding the equations for this topic. Okay, it has now been 5 minutes, and hopefully you've been able to spend some time trying to review as many equations as you can from this topic. As I said, hopefully you should be fine. So now we're going to go over them. I did not do blurting for this myself because I wanted to go through all of them with you to make sure you knew all of the equations because they're all quite important. So let's go through the equations now. So first of all, let's just define what number of moles is, and what moles is. So first we have this idea that we have of the relative atomic mass. So the relative atomic mass is the average mass of the isotope of that element weighed to take into account the abundance. So remember, we did this in yesterday's chemistry session. So relative atomic mass is the average mass when taken into account the different isotopic masses, as well as taking into account the abundances of each isotope. Now we have relative formula mass. So what is relative formula mass? Because this is quite different. So relative formula mass is a sum of the relative atomic masses of the atoms in the numbers shown. So sum of the relative atomic masses. So say if you wanted to find the relative atomic masses of the reactants, it would be the relative atomic mass of each element added together. Okay, hopefully that makes sense. So now we're going to look at what moles is. So the key equation in this topic is the number of moles is equal to the mass of a substance divided by the mass of 1 mole of a substance, which we know as MR. So the mass of 1 mole of a substance is the number that you have. So when you see, for example, lithium 7,3, the mass number, so this very number here, is the mass of 1 mole of this. So 1 mole of lithium is 7. That's what it means, basically. And the mass is how much you have of it. So that's the key equation. So when we go through key equations, I'm just going to put them as triangles because I know some people like learning from triangles. So number of moles is equal to mass divided by the mass number. It's the key equation there. Now we also have another equation. Now, just so you note and don't get confused, the mass number is exactly the same as the relative formula mass of just one element. So the mass number, the relative formula mass, is the total mass number of all of the elements added together. Now, if you're doing reacting acids, which is quite an important skill, so we had the question that was like this: magnesium plus hydrochloric acid creates magnesium chloride plus hydrogen. So you're given 192 grams of magnesium and you're being asked to work out how many grams of hydrogen. So firstly, what you want to do is say, let's write it in green. So you want to create a column for the masses you want to create a column for the mass number, and then you can create a column for the moles if you wish. So the moles are represented by the big numbers in the front. So here you can see that there are 2 moles. So 1 mole of magnesium, 2 moles of hydrochloric acid, 1 mole of magnesium chloride, and 1 mole of hydrogen. Now, in terms of the mass numbers of magnesium, it's 24 in the periodic table. For hydrochloric acid, hydrogen plus chloride times 2 would be 73. And then magnesium chloride would be 95. And 2 for hydrogen. And a way to check this is correct is the total of this and this, the total of the reactants, should equal the total of the products. So now, and we're told 192 grams of magnesium. So if you've got 192 grams of magnesium, to find the amount of hydrogen, all you would do, and knowing the equation of moles is equal to mass over mR. In this case, we've got 2 and 1, and the mass is unknown. So mass of hydrogen is going to be moles times mR, which is 2 times 1, which is 2. But what you do instead in this account is, because you're given the mass of magnesium, you want to compare that to the mass of hydrogen. So 192 divided by 24 is equal to 16. And yeah, that would be your answer. So, moving on to another equation now, which is concentration. So concentration is equal to mass over volume. Now you can think of this visually if you want. If you can imagine how concentrated a substance is how much of something there is within a specified area. So if you box here, the box has a certain volume, so which is just height times length times base, and inside there will be a mass of a different substance. So say if you're trying to find the mass of, I don't know, a number of cakes, for example, in this box. So the cakes could be like this. So how concentrated this is the number of cakes in comparison to the volume. So how much mass there is, how much cakes there are in the volume of the box. That is what concentration is. Concentration is mass over volume, and the mass has the unit grams, and the volume has the unit decimeters cubed. Now, just regarding the 2 equations we've looked at, there's already another rule that you need to be aware of. And it's the idea that to convert from moles per decimeter cubed, you're converting from moles to mass. It's the same thing. So we're going to use the equation of number of moles is mass over mR. So to convert it, you convert the moles to the grams. To convert the moles to the grams, you're going to have to times it by the mR. So moles per decimeter cubed times by the mR would give you the grams per decimeter cubed. And that's how it would work. Now you're often given titration questions, which you have to do calculations in. So we can look at a titration. So 20 centimeters cubed of potassium hydroxide is placed in a flask. It's placed in a flask. Using an indicator, it was titrated against hydrochloric acid of concentration. So let's create a table using the information that we hear. So whenever you have a titration calculation question, it will normally give you a volume, concentration, and mass. Perhaps mass, either mass or moles. I'll do columns for both in this case. So we have used, this is the alkali, and 20 centimeters cubed of potassium hydroxide is titrated against hydrochloric acid, and this hydrochloric acid has a concentration of 1 mole per decimeter cubed. Now notice, and do not forget to notice, that centimeters cubed and decimeters cubed are two different, so there will definitely need some conversion taking place. I can give you the conversion at the top here, that 1 centimeter cubed is equal to 1,000 decimeters cubed. Or, sorry, it's the other way. Actually, 1 or 2, 1,000 centimeters cubed. Nope, it was the right way immediately. In 1 centimeter, there's 1,000 decimeters. Yeah, that sounds right. That's right. So now we've got the volume and of the potassium hydroxide and the concentration of hydrochloric acid. After repeated tests, it was found that the potassium hydroxide was neutralized by 12.5 centimeters cubed of hydrochloric acid. So now we have the volume of hydrochloric acid. What is the concentration of potassium hydroxide? So now we can circle what we are asked to find. So in order to find the concentration of potassium hydroxide, we can use our equations. So let's just write off our two equations that we've learned. So we've learned that moles is equal to mass divided by mR, and we know that concentration is equal to mass over volume. Now firstly, let's convert both of the volumes into decimeters cubed, because this is what this is measured in. So it's much easier to do it that way around. So 20 centimeters cubed to decimeters cubed. Let's just do that up here. Is 0.02 decimeters. So ignore that. 1 decimeter cubed is equal to 1,000 centimeters cubed. 1 centimeter is equal to 10 decimeters. So 0.02 decimeters cubed, and hydrochloric acid, so 12.5 divided by 1,000 would be 0.0125. I don't know why I'm writing in the wrong column. 0.0125 decimeters cubed. So now we have the volumes of both of them in the correct units. We can now work out the mass and moles of hydrochloric acid. So we're given the volume and we're given the concentration, so we can actually work out the mass by doing 0.0125 multiplied by 1, because that will give you the mass, and therefore we know, and it's also equal to the moles as well, moles or mass. So then we know that there are 0.0125 moles. So ignore this column for now. And when we're looking at hydrochloric acid, we know that in the reaction they're the same. They have 1 mole each. So if we put this there, 0.0125, we now know the mass and we now know the volume. Do mass over volume, 0.0125 divided by 20, and you get, or divided by 0.02, remember to convert it, and you get 0.625 moles per decimeter cubed. That's how you would answer it. Titration question. And just to finish off, some final equations that not necessarily are as complex as the ones we've just looked at. So the first one is percentage yield. Now percentage yield is the actual mass over the theoretical mass times by 100. So what this is saying is, it's saying if you were to actually carry out an experiment, obviously some mass would be wasted because it's not as perfectly going to be carried out. There will be some human error and things like that. So the theoretical mass is basically the calculated mass of what you would receive, and your actual mass is what you got in your physical thing. And you times about 100 and you'll normally get a percentage of how well you did. Now you have the other equation, which is percentage atom economy. Now percentage atom economy is the relative formula mass of the desired product over the sum of the relative formula masses of the reactants, and then times 100. So atom economy is telling you how much of your desired product is made from all of the reactants. Now the closer this number is to 100, the better. And finally, after these two equations, we have number of moles in a gas, and the number of moles in a gas is equal to the volume divided by 24 decimeters cubed. So if you want to just go over it one more time, go over all of the equations we have looked at today. So moles is equal to mass divided by mR. We have got that concentration is mass divided. We've got percentage yield is actual mass divided by the theoretical times by 100. And we've got percentage atom economy, which is the relative formula mass of the desired product over the sum of the relative formula mass of the reactants multiplied by 100. And that's the 4 equations key to quantitative chemistry. Now, you can find loads of questions on this on exam question websites. This topic, there's much less of of revision as there is to practicing this topic, and that's why it would require more practice than anything. So next session for this topic that we're going to do, because we're going to go over this 3 times, so the next 2 sessions we'll just be doing practice on this topic. But for now, let's move on to the next topic, which is, drumroll, chemical changes. Things like acids, bases, making salts, again titrations, and then electrolysis. So this is the one that people often start to stumble on in paper 1. So let's go. I'm going to give you 10 minutes up until 6:35 to write as much as you can remember about this topic. Okay, everyone, if you are done, hopefully we're now going to go over them. So make sure if you've missed anything, write it in a different coloured pen. And let's get started by looking at what we can write. So the first requirement was talking about acids and bases. So hopefully you mentioned what an acid is, what an alkali is, and what a base is, and what the differences are in them. So let's just zoom in here, and hopefully you've mentioned the pH scale as well. So the pH scale goes from 0 to 14 and is a measure of how acidic or alkaline it is, but in reality it's just a measure of the hydroxide ions. An acid is a substance that forms hydroxide ions, hydrogen ions, and alkaline. And that's where we have the ionic equation. So this is what you would call the ionic equation. That the H plus ions in an acid react with the OH minus ions in an alkali to form something neutral, water. And that just shows us the ionic equations of neutralization reactions. We then look at titration, which is when you're finding out how much acid or alkali needed to neutralize the solution. You have your burette, you have your conical flask, you might even want to have a white tile if you wanted to. And you use indicators. Now we look at strong and weak acids. So strong acids ionize in solutions. So acids ionize in solutions because they produce hydrogen ions, right? So what we mean by whatever ionizes is acids ionize, they literally produce ions. So if we look at hydrogen chloride produces a hydrogen ion and a chlorine negative ion. So that's how it works. Or if you have HNO3, this produces again a positive hydrogen ion and then negative NO3. So in any aqueous solution, which just means dissolved in water, acids ionize. Now, a weak acid therefore means something that partially ionizes, does not fully ionize. Now, in exams, they often describe this as they do not fully dissociate. Whereas strong acids fully dissociate. Which is why when strong acids are put into an aqueous solution, it's not reversible, but when weak acids are, it is reversible because it does not ionize fully and does not dissociate fully. Now, reactions of acids involve the H plus ions reacting with other substances. So if the concentration of H plus ions is higher, the rate of the reaction will be faster. So strong acids will be more reactive than weak acids. Okay. Now, as we said, pH is just a measure of the hydrogen ion, so not hydroxide, the H plus ions within a solution. So, for example, pH1 has a certain volume of hydrogen ions, then pH2 will have 10 times less hydrogen ions because it's less acidic by 10 times. And it continues up until pH 14. Now, don't confuse pH strength with the concentration of acids, because a strong acid can be diluted, because the strength of an acid depends on whether it can fully ionize and fully dissociate, whereas the concentration of an acid is dependent on how much mass of an acid there is in a volume of water. So if there's a lot of acid in a volume of water, we call it concentrated. If there's not enough acid mass in a volume of water, then we call it diluted. So it's possible for a strong acid to be dilute. Okay, now it's important to know reactions of acids. So we looked at reactions of acids here. So acid plus alkali creates salt and water. Acid plus metal creates salt and water. And when we talk about acid plus metal oxide, so acid plus metal oxide or acid plus metal hydroxide equals salt and water. And then acid plus metal carbonate equals salt plus water plus carbon dioxide. Now, there are loads of examples on this for you to revise on this. But now moving on to the reactivity series. So the reactivity series is just a list of metals in order of their reactivity towards other substances. So if you're comparing the reactivity of the different metals with either acid or water, and you're putting them from most to least, this is the list that you get. So if you were to react metals with acids and rate their reactivity, this is exactly the order that you would get. Now, metals react with acids tells you a lot about how their reactivity. So just reforming this, we've got acid plus metal oxide or hydroxide. Now, because there's an oxide or a hydroxide, this means that you can produce salt and water. But if you were just reacting acid plus metal without oxide or hydroxide, you would just get salt plus hydrogen. There's no oxygen there in that equation, so you can only create hydrogen. And if you're reacting acid plus metal carbonate, as we said, you will get salt plus water plus carbon dioxide. So you can see how it can be very confusing in terms of the acid plus metal reactions producing 3 different products. So you need to remember when you're looking at a question, is it a metal hydroxide or oxide? Is it just a metal, or is it a metal carbonate? And then make your decision from there onwards. Now, metals also react with water as well. And water and metals produce metal hydroxide and hydrogen. Okay. So now we've looked at the key reactions. It's important to look at separating metals from metal oxides. So metals often have to be separated from their oxides, and this can be done through reduction, which again links back to the reactivity series. So we've got reduction with carbon, which is also, in other words, often known as, instead of reduction, is often known as displacement reaction. So the ore is reduced as oxygen is removed from it. So let's look at an example of reduction. So we have plus carbon creates iron and carbon dioxide. So here, if we're looking at this reaction, we see that iron is the core because it's reacted with oxygen, so it's a core. And by reacting it with carbon, what you're doing is then you're separating this oxygen, you're getting rid of the oxygen through reduction, and carbon dioxide a reaction and iron does. But this if the metal and the iron core here is less reactive than carbon, because oxygen will only ever want to go with the more reactive, right? So if iron is more reactive than carbon, then it would never move to carbon, if that makes sense. Okay. So that therefore means, though, that not all metals can be reduced by carbon. Only the metals that sit below carbon, so zinc, iron, lead, hydrogen, copper, silver, gold, can be reduced via carbon. Some, and especially these, however, silver and gold, these are actually unreactive. So silver and gold won't even be able to be reduced, but the other ones would. Now, there's other ways to extract them through electrolysis, but let's just quickly look at redox reactions and what redox reactions are. So a redox reaction is just a normal reaction because you have the reduction and you have the oxidation. And reduction is losing electrons. And oxidation is gaining electrons. And in every equation and every reaction you have a lot of it is redox because some elements are losing electrons and some are gaining electrons. So displacement involves kicking another one out, which we already discussed with the copper. In displacement reactions, it's always the metal ion that gains electrons and is reduced. Ionic equations just focus on the useful bits of the reaction. So ionic are things like when we looked at the ionic equation for acids and alkalis, it just shows and focuses on the most important bits. Now we're going to focus on electrolysis and electrolysis of aqueous solutions. So let's go on to electrolysis. So electrolysis works for and is used by everything that sits above carbon in the reactivity series because it cannot be reduced by carbon. So everything than carbon. So how electrolysis works is just splitting something up with electricity. So what you have is you have a solution, or you have the solution and you have two blocks. We call these electrodes. Now, the solution is what we call the electrolyte. The electrolyte is a molten or dissolved ionic compound. What does that mean? Molten or dissolved ionic compound. So whatever you're trying to split up, so say if it was aluminium oxide, what you would do is you would physically melt the aluminium oxide. So that's where molten comes in. And dissolved is just when it's not necessarily in water because that would be an aqueous solution. Yes, all right. Dissolved ionic compounds would be in electrolysis of aqueous solutions, which we're going to look at soon. So the electrolyte is a molten or dissolved ionic compound. Now we have electrodes. Now electrodes can be positive or negative, and you need a positive one and a negative one, because what happens is the ions within the electrolyte move towards the opposite charges. So the negative ions move towards the positive, and the positive ones move towards the negative, because opposites attract. And this therefore separates the compound into these separate elements. The positive ions in the electrolyte will move towards the cathode, which is the negative, and the anode, which is the positive, will attract the negative ions. Now, because there is a charge difference, this therefore creates a flow of charge through the electrolyte as ions are now traveling. So as ions move around, a charge is created. And what happens is, as ions gain or lose electrons, they form the uncharged element and are discharged from the electrode. So what happens is, in a normal reaction, the elements change to ions in order to gain electrons to get a full outer shell. Now, in electrolysis, we're going from ions to elements. So we're going back to the original state. And in order to go back, there will be electrons, free electrons, which will be at the electrodes. Now, an ionic solid cannot be electrolyzed because of the fact that the ions are in fixed positions and cannot move. So this only works if it is molten. A molten can work because the ions can move freely, and therefore the ions can conduct electricity. And it's all about ions. Don't say electrons, say ions, because it's the charged particles, not just the electrons themselves. Now, if a metal is too reactive to be reduced with carbon, then electrolysis is required to extract it. So it's important to know the different steps of extraction via electrolysis. Aluminium is extracted from the ore by electrolysis. Now, the aluminium oxide has a very high melting point. So the aluminium is extracted from the bauxite. But unfortunately, aluminium has a very high melting point. So what happens is it's mixed with a substance which we call cryolite, which lowers the melting point. And after lowering the melting point, what happens is the molten mixture now contains free ions. These free ions are able to move around, and therefore electricity will be conducted. So as we said, aluminium is extracted from its bauxite, but we have aluminium oxide, and we need to separate the aluminium and the oxide. But the aluminium has a very high melting point, so we add cryolite to reduce the melting point, and then electrolysis happens. You create a molten mixture, and the free ions that move around towards the electrodes move towards, and electricity will be conducted. So the positive Al3 plus ions will go to the cathode, and the negative O2 2 minus ions will go to the anode. And there are different equations for each one. So at the cathode, there will be a certain equation. So you have the ion to begin with. And what we want is the ion to turn back into the element. So to turn back into the element, you need to get rid of these. You need to add 3 more electrons back to it, and you get aluminium. Now, in terms of the anode, you've got OT. In order to become oxygen again, then you need to take away the electrons at the end. But oxygen exists as a molecule, so you will put a 4 here. Sorry, you'll put a 2 there and a 4 here. And that's how it would work in that case. Now, in terms of electrolysis of aqueous solutions, it's a whole nother story. The issue with electrolysis of aqueous solutions is because it's in water, the water now interferes because there's more ions. There's hydrogen ions and now there's hydroxide ions. So on top of the metal ions going to the cathode and the non-metal ions going to the anode, we also now have the hydrogen ions and the negative hydroxide ions, which would be going to the same places. So there's now 4 ions to deal with, and that is why it becomes more complex. However, don't worry, because we are here to simplify it for you. So at the cathode, we now have the metal ions and the hydroxide ions, and therefore hydrogen gas will be produced if the metal ions form an element that is more reactive than hydrogen. So now we have rules, okay? So let's say we've got the cathode. So at the cathode, we've got the metal ions and the H plus ions. These are both positive, by the way. So what happens is what is produced is hydrogen. Hydrogen gas is produced. But hydrogen gas is only produced if the metal element that is produced is more reactive. So hydrogen gas is produced if the metal is more reactive than hydrogen. So let's go through that again. At the cathode, we have the metal ions and the hydroxide ions because they're both positive. And what is produced is hydrogen gas, but hydrogen gas is only produced if the metal is more reactive than hydrogen. If the metal is less reactive than hydrogen, then what would happen is a solid layer of the pure metal will be produced instead. So if the metal is more reactive than hydrogen, then hydrogen is produced. Because if you think of it, hydrogen will only be produced if it's unable to displace the metal. However, so therefore, because it's unable to displace the metal, hydrogen is produced. However, in this case, if the metal is less reactive, it can easily displace it, and therefore a solid layer of metal is produced instead. Now, anode equally has its own rules. So at the anode, we see the non-metal negative ions, and we see the hydroxide ions. And the rules are with this, that oxygen is produced as long as there are no halide ions present. So if the nonmetal is a halogen, then no oxygen will be produced. But if the metal is not a halogen, then oxygen is produced and the OH minus ions are discharged. So we can apply our understanding to this situation here. So if we look at the copper sulfate is being electrolyzed here. So we have the anode and we have the cathode. So at the anode, which is the positive, we're going to see the metal ions, the negative metal ions, or the positive metal ions, sorry, as well as H+. Now, copper, as we know, is less reactive than hydrogen. And therefore, because it's less reactive, you will see a pure, solid layer of copper. At the cathode, we have a sulfate ion. Now, there are no halide present. There are no halides. And when there are no halides, that means that oxygen is produced and that the OH minus ions are discharged. So if we have to write equations of what happens at each electrode, at the cathode, we'll say we have copper ions, and then we have these copper ions then add 2 electrons to return it to its natural state, which is just copper. And at the cathode, we have, because there's no halides, it will be 4OH, 4 hydroxide, which produces oxygen plus water plus 4E minus. This one is much easier to just learn. And if the anode, the metal, was more reactive than hydrogen, then you will see 2H plus 2E minus creates hydrogen. So we'll see hydrogen being produced and we'll see oxygen being produced. And that is it for chemistry. So now we're going to move on to physics. And I'm going to give you 10 minutes, as usual, to go through as much of the topic. We went through energy yesterday. We didn't get a chance to go through electricity, but we have to keep going, as usual. So you have until 7:15 to write as much as you can. Or this is a small topic, actually. So we'll say up until 7:10 to write as much as you can about this topic. Okay, hopefully you've now had time to just do some quick revision over particle model of matter. This topic is quite small, there's not much to do about it, which is good because we can fit in yesterday's topic that we missed about electricity, hopefully in here after we do today's topic. So, first of all, starting off with density. There's a key equation for density, which hopefully you should know. Density is equal to mass over volume. That's the first equation. Let me share the screen with you. So there's just a key few principles in this topic, which I will bullet point for you. So the first one is that density is equal to mass over volume. That's just the equation for density. And the density of an object depends on what it's made of and how particles are arranged. So it has a lot to do with the arrangement of particles and what it's made of. So in terms of solids, liquids, and gases, solids will have a dense, packed particles in fixed positions that the movement permitted is vibration. Then we have liquids, which have weaker forces of attraction between them and therefore are more distant. The particles are close together and can move past each other, but they have irregular arrangements. And gases have almost no forces of attraction between them. They're less dense and they can move at very high speeds. Now, measuring the density is actually required practical in this topic. So let's just quickly go through it. So we have something in science called a eureka can. And this is used mainly in this required practical to measure the density of irregular shaped objects. Because normally density can be found by doing normally the density can be found by using a balance to measure mass and then using a ruler to measure the volume of something like a cube, for example. But however, it's very hard and difficult to measure the volume of an irregular shape such as like a star. So you can do this through using the eureka can. So the eureka can will be filled up with water up until the spout. And what you do is on a string, you lower the irregular shaped object down into the water, and then there will be water that pours out through the excess through the spout. And the volume of water that is poured out as excess through the spout is actually the volume of the object. And once you know the volume of the object and you can measure the mass, we know that density is equal to mass over volume, so you can easily work it out. That is a required practical, but there's not much to learn about it apart from just the function of the eureka can. Now we need to know about internal energy and changes of state. So the particles in a system vibrate or move around. They have energy in their kinetic energy stores. So we have kinetic energy stores. Kinetic energy is energy stored in motion. However, there's also some stores called potential energy stores. Potential energy stores. And potential energy stores is the energy stored in your position. So just think of kinetic energy and potential energy as opposites. Kinetic energy is in motion and potential energy is in position. Now, the energy stored in a system is stored by its particles. The internal energy of a system is the total energy that its particles have in their kinetic energy and their potential energy stores. So internal energy, therefore, is the total energy of the potential energy stores. So it's the total energy of a system, quite literally. Now, heating the system When you heat it, it transfers energy to the particles. They then gain energy in their kinetic energy stores and move faster. This then increases the internal energy. This leads to a change in temperature or a change in state. If the temperature changes, the size of the change depends upon the mass of the substance. What it's made of, its specific heat capacity, which we looked at in yesterday's live. Make sure you all this stuff on specific heat capacity from yesterday, as I said. So let's just go through that again. When we're heating up a substance, we're therefore increasing the internal energy of the system due to the fact that we're increasing the kinetic energy at which it's moving, and the potential energy remains constant. And when we increase the kinetic energy, we increase the internal energy. And when we increase the internal energy, this then leads to one of two things. It can either increase in temperature or it can change state. So that's just a summary of what we've just looked at. So a change in state overall occurs if the substance is heated enough that the particles have enough energy in their kinetic energy stores to break the bonds that hold them together. So changing state requires a certain amount of kinetic energy, which will help to break the bonds, and this is referred to as the specific heat capacity. You can watch yesterday's live stream if you're unsure about that topic. Now, when you heat a liquid, it boils or evaporates and becomes a gas. So in this topic, you just need to know the basic conversions from solid to liquid to gas. Solid to gas and gas to solid are the rare ones. And that's why that's the only ones I'm going to go over, because the other ones should be obvious, like evaporation and freezing and melting. So when you're going from solid to gas, it's called subliminating. So that's from solid to gas. Now, when you are changing a state, it's a physical change. It's not a chemical change. So you don't end up with a new substance. It's just the same substance, but in a different form. If you reverse a change of state, then the substance will return to its original form with original properties. The number of particles does not change, it's just the arrangement that changes. So a change of state is just a physical change to the arrangement of the atoms. Okay, now we've gone over that. Let's look at one of the other principles, which is all about specific latent heat. Now, specific latent heat is the amount of energy required to change 1 kilogram of substance into another state without increasing the temperature. So is the amount of energy to change this state of a substance without changing its temperature. Now, you may be confused as to how can something change its state without having changed its temperature. Well, let's look at the heating and cooling graph that you should hopefully be familiar with. So a heating graph tends to look like this, and a cooling graph looks the opposite. So in this heating graph, on the y-axis, we have the temperature, and on the x-axis, we have the time. So between this point and this point, it's going from, it's a solid. So let me write that here. Between this point and this point, it's now a liquid. And between this point and this point, it's now a gas. So what happens at the stationary points in between? Well, if you notice that between this time, we must assume that it changes state from solid to liquid. However, we notice no change in temperature, and we also see this in liquid to gas. We see that as it changes state here, there is no change in temperature. Now, why is this? Why is there no change in temperature when we're changing states? Let's try and explain this. So when we are inputting energy and heating a system, what happens to this system is that we are inputting energy, but when it starts to change state, this then means that you're putting energy into increasing the internal energy. So when you're heating a system, you're putting energy in, which therefore increases the internal energy of a system. But the energy used for breaking intermolecular bonds rather than raising the temperature. Energy can either be used to increase the temperature, or energy can either be used to break the intermolecular bonds. Now, one thing to note is that energy can never be used to increase the temperature and break intermolecular bonds. It's one or the other. So when we're changing state, it has to be this energy that it's being used in, and therefore there is no increase in temperature. However, when we're not changing state, it therefore means that it has to be the increase in temperature and no change in state. Now we will see the same thing in a cooling graph. So in a cooling graph, you're decreasing the temperature. So at this point, it's a gas. At this point, it's a liquid, and at this point, it's a solid, which then means that at this point, it's condensing from gas to liquid, and at this point, it's freezing from liquid to solid. So we've got gas, liquid, solid. And the same rules apply here, that you see there is no temperature change when we're changing state. So we see that all the energy inputted is, or actually in this case, it's being released, isn't it? So all of the energy released is either used to decrease the temperature or to create bonds. Now so when energy is being used to increase the temperature or to decrease the temperature, then you will see at this point gas, at this point liquid, at this point solid. But then at the straight points where the temperature does not change, then the energy is then used to be creating bonds and the temperature does not change. Hopefully this makes sense. If it doesn't make sense, feel free to put it into the chat. And that's all you need to know about specific latent heat. Oh, well, sorry. You are going to be given the equation for specific latent heat in the exam. However, it's always good to be familiar with it. So the equation for specific latent heat is energy divided by mass. Sorry, I just had to convert it in my head. So that just means that energy is equal to mass times specific heat capacity. Specific latent heat. So unlike specific heat capacity where there's loads of there's loads of elements required. So specific heat capacity requires change in temperature, change in mass, and things like that. This is just energy and mass. There's no change in temperature. So that's how you remember that specific latent heat is the amount of energy required to change the state of a substance without changing its temperature. This topic is just looking at particle motion in gases. So let's just revise that. This is a relatively simple topic, so hopefully you should fly right through this. Now we know that in solids, particles move by vibrating because that's the only movement that they can happen, and this then causes the kinetic energy stored to increase. In liquids, particles can move and flow, but in gases, it's a whole nother thing. Because there are such weak and barely any forces of attraction, these particles are constantly moving in random direction and at random speed. So that means that if you increase the temperature of a gas, then you transfer energy to the kinetic stores. So increasing the temperature of the gas increases the kinetic energy stores of the gas. And if you increase the kinetic energy stores of a gas, then it will then be moving faster. Now, the temperature of a gas is related to the energy in the energy stores of the particles. Faster and an increase in internal energy. So the higher the energy, the higher the temperature of the gas, or the higher the temperature, the higher the energy, because the faster it starts to move. Now, as gas particles move about at high speeds, they bang into each other and whatever else happens to get in the way. When they collide into something, they exert a force. So imagine in a sealed container, we have gases. A gas are colliding with the wall, exerting their energy as a force. So the outward gas pressure is therefore outward gas pressure is therefore the total force exerted by the high energy particles. Faster particles and more frequent collisions will lead to an increase in net force and increase in pressure. So if we increase the kinetic energy, this will then lead to an increase in pressure. And if we increase the collision frequency, so how often they bang into each other, then you're increasing the pressure there as well. You get the equation. Pressure multiplied by the volume is equal to a constant. So it's just suggesting that pressure and volume are inversely proportional. When you increase the volume, you are decreasing the pressure. And when you increase the pressure, this must lead to a decrease in the volume. So in terms of pressure, just to help you understand, imagine we have a balloon here. Oh, that's a terrible balloon. A helium balloon. If a helium balloon is released, it rises. So we have helium particles in here. So imagine it's helium, 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 helium. So once it's released from a force, it then rises up. The atmospheric pressure then decreases with height. So the pressure outside the balloon then decreases. This causes the balloon to expand until the pressure inside drops to the same atmospheric pressure. So what it's saying is, as the balloon moves up and up the room, the atmospheric pressure at the top of the room decreases. So there's a lot less pressure. The balloon neither also remain constant with the pressure outside. It wants to have the same pressure inside the balloon as it does outside the balloon. And how it solves this is by changing its pressure. So it decreases the pressure inside the balloon by expanding. So the higher the balloon goes, the more it expands as it tries to catch up with the atmosphere around the balloon. Now, I hope that makes sense. And that is all we need to know for this topic. So, particle model of matter is all done. I assume that would take quicker, but I just wanted to make sure you knew everything. Now, the next task is we're going to be looking at atomic structure. So this is all about radiation, nuclear equations, half and fusion. So what I want you to do is spend 10 minutes writing as much as you can, blurting out everything you can remember, using these 7 prompts to help you out there. And then after 10 minutes, we will go through. Good luck. Hey everyone, I'm back and I'm not sure if you've completed this, it's quite a lot to cover, but we're going to go through it together now. If you have missed out anything, ensure that you do change a different colour pen and add it to whatever you've written. And instead of adding to what I've already written, I'm just going to go over the entire to forget. So let's begin. Atomic structure. So just some key facts that you may need to know. The radius of an atom is 1 times 10 to the power of minus 10 meters. That's the radius of an atom. But the radius of a nucleus is 10,000 times smaller than that of an atom. So what this is just trying to tell you is how small it actually is, how small the nucleus is in relation to the atom. Now, what happens is when an atom absorbs electromagnetic radiation, electrons can move. So when we have an atom and we have electromagnetic radiation, electromagnetic radiation basically causes electrons to move about. It can move from a lower energy level to a higher energy level, release its radiation, and then return back to where it originally has. And that's just some background information as to how some radiation works. Okay, let's just clear that. So, an isotope, as you should know in chemistry, is atoms of the same element, just with a different number of neutrons and therefore a different mass number. Now, isotopes can sometimes be unstable. Sometimes isotopes can have an unstable nuclei. Because of the different number of neutrons, it can sometimes change. Unstable nuclei. Now, unstable nuclei, as everything in chemistry says, anything unstable wants to become stable. It wants to stabilize. So a atom wants to gain a full outer shell. An unstable nuclei wants to go back to being stable. Now, in order to go back to being stable, it undergoes a process which we call radioactive decay. Now, how do we define what radioactive decay is? Well, radioactive decay of a nuclei, of an unstable nuclei, releasing radiation to become stable. So radioactive decay is when there is an unstable nuclei that releases radiation to return to how stable it was previously. Now, we have certain rates of radioactive decay that we need to know about. So, the first one is what we call the activity. Activity is the rate at which a source of unstable nuclei decays. The rate at which a source of unstable nuclei decays. So this is measured in something called becquerels, which is written as BQ. And what it means is 1 becquerel is 1 decay per second. So activity is the rate at which a source of unstable nuclei decays. We also have another measure, which is called count rate. Now, count rate is hugely similar. Count rate is the number of decays per second recorded by a detector. a count rate of 24, that's saying that there's 24 decays that have happened within 1 second. When you say the rate at which a source of, when you say the activity is 10 becquerels, that's also saying there's 10 decays per second. So it's very, very similar, apart from the main fact that activity has a unit becquerels, whereas count rate is just the number of decays recorded per second. Now, there's 4 types of radiation that you need to know of. So let's look through them. They all have different properties as well. Okay, so let's look deeper. So the first one is what we call alpha radiation. It's represented by an A. In exams, if you see an A, that's referring to alpha radiation. And an alpha radiation is just composed and 2 neutrons, which i.e. is just a helium nucleus. So alpha radiation is literally just a helium particle. It's the same nucleus as a helium. The second type of radiation is called beta radiation. It's represented by a B that looks a bit like that. Now, beta radiation is a very high-speed electron that is ejected out of the nucleus. So this very, very high-speed nucleus, very high-speed electron. So alpha is basically a helium nucleus. Beta is basically an electron. Now we also have 2 more. So we have number 3, which is gamma radiation. Now gamma, ironically, has nothing to do with a G, it's a Y, gamma radiation. And the 4th one is neutron radiation. You don't tend to be asked about neutron at all, but it's good to know that it's there. And gamma radiation are literally just electromagnetic radiation. So view gamma radiation as waves. So if we were to draw out each of them, then I would describe alpha as something with 2 protons and 2 neutrons, like this, and just say helium. So that's how alpha is just an electron that's very fast. Gamma is a wave, and neutron you don't really need to know about. So they're the 4 different types of radiation. Okay. Now it's also important for you to know about the properties of each type of radiation because they have differing properties. So in this case, you're only going to know about alpha, beta, and gamma properties. Neutron is not necessary. So in terms of properties, you have to compare the range in air, so how far it can travel in plain air. And then the second one is the penetrating power, which is how easily it can penetrate through an object or material. So is it able to penetrate through a brick wall, or is it able to penetrate through paper? And finally, ionizing power. So ionizing is when electrons are knocked off, and it's very bad. If we have ionizing radiation for humans, knocking off electrons can have really bad effects because it can trigger you to get your tumor cells to start fusing and form cancers. So that's why ionizing radiation is not very good for you at all. So let's look at the properties. So alpha particles, you can imagine, is a helium nucleus. So this is the heaviest because compared to a small beta electron or a wave, alpha particle is definitely the heaviest. So because it's the heaviest, it can only travel 5 centimeters in air, which is very small. Less heavy, it's an electron, so it can travel 15 centimeters in air. And gamma radiation is literally just a wave, so it can travel several meters in air. Now, penetrating power. So the alpha particle or helium nucleus is the biggest. Therefore, it's unable to penetrate because something smaller is more able to penetrate through something rather than something bigger. It's more likely to be blocked. Therefore, the penetrating power of alpha radiation is very little. And what we call it is it can go through a single sheet of paper. Beta radiation can travel a few millimeters and can be a few millimeters of aluminium as well, so metal. And gamma radiation can travel several centimeters of lead. And lead is the thing that tends to stop most radiation, which is why people wear lead gloves and lead aprons when they're handling radiation. So in terms of range in air, gamma has the highest range in air, alpha has the lowest range in air. In terms of penetrating power, gamma has the highest penetrating power, alpha has the smallest. But in ionizing power, it now flips. So ionizing is how likely it is to knock off electrons. Now, because alpha is the biggest, it actually has quite a highly likely to knock off electrons. So it's very strongly ionizing. Beta is in the middle. It's still quite strongly ionizing, not as strong as alpha. And then gamma is very weakly ionizing because it's only a wave, so it's very difficult for it to force an electron out. And those are the properties of the 4 types of radiation. Now, knowing these facts and knowing what alpha radiation is composed of and beta radiation is composed of, being 2 protons, 2 neutrons, and 1 electron, you will be asked about nuclear equations, and you'll be asked nuclear equations. So this is when you just have to predict what radiation is going to happen to something and what it will produce. So let's start with alpha. So alpha radiation, as you can remember, is composed of 2 protons and 2 neutrons. And when we are doing the equations, we can just imagine that it's a helium nucleus, which has 4 as its mass number, because mass number, remember, is protons plus neutrons, and 2 plus 2 is 4, and then 2 as its atomic number, which is the number of protons. So you'll be given questions like this. So you'll be given this information and you will be allowed a periodic table, and it will say, what does it produce? What are the numbers? And you have to describe the numbers. So they'll be like, alpha radiation happens to radium here. What does it produce? And what you have to figure out is, well, you know alpha radiation always produces a helium, and you know that helium has got the values 4 and 2. And since it's separated from helium, this value will be 226 minus 4, which is 224. And this value will be the number of protons, and the number of protons will be 2 less, so it will be 86. And that's how alpha radiation works. When we're looking at beta radiation decay, hopefully that makes sense. I know it may be confusion. We know that beta is a very high speed electron, and how it is ejected from the nucleus. So an electron has the mass number of 0 because it's not made of protons or neutrons, and has the -1 charge. So when we're asked calculate or describe the beta decay of aluminium, what you would say is aluminium, we know that beta would produce an electron, so it'll be 0 and -1. So nothing will change with the mass number, but the atomic number will increase by 1. Don't say decrease, it will increase, because if you're adding an electron, then that means that you have an extra atomic number, and therefore you get silicon. Hopefully that makes sense. Please put it in the chat and I will help you out there. But that is it. And then you won't be asked about gamma calculations because gamma is just an electromagnetic wave, so there are no calculations to do. Now it's important to know more about activity, count rate, and half-life. So half-life is one of those odd things in physics that has two definitions. So half-life is the first definition is the amount of time a radioactive isotope takes for the nuclei to halve. So the amount of time taken for the nuclei to halve. That's the first definition. The second definition is the time it takes for the count rate to fall to half its initial level, so to also halve. So remember when we said here that the count rate is the number of decays per second. So half-life is the time it takes for the number of decays per second to reduce by half, and half-life is also the amount of time taken for the. So let's try and do a question here so that we know what we're talking about. So the question will go like something like this. A radioactive isotope has a half-life of 15 days and an initial count rate of 200 counts per second. Determine the count rate after 45 days. So in this question, we're given the half-life, 15 days. So this is how many days it takes for the count rate to halve. And we're given that it's been 45 days. So we're asked what is the count rate after 45 days? So let's plan a timeline. So after the first 15 days, we know that the count rate is going to be 200 divided by 2, which is 100. Then after 30 days, so another 15 days have passed, this count rate halves again. 100 divided by 45 days. So 45 days, so another 15 days, the count rate halves again to 25. So the count rate after 45 days is now 25 counts per second. Okay, finally, of this topic, we're going to look at irradiation and contamination, and then we'll move on to fission and fusion in a second. So irradiation is when when you expose an object to nuclear radiation purposely. So purposely exposing a material to nuclear radiation. Now you may do this in order to get rid of certain like bacteria or microbes and things like that. For example, to sterilize objects. And you have to take certain precautions. So if you're using alpha radiation, you'll use gloves. If you're using beta and gamma, you'll use a lead apron and things like that. Now, contamination, on the other hand, is the accidental exposure of materials to nuclear radiation. So it's basically the same thing as irradiation, but it was not supposed to happen, and therefore it can cause very bad things to happen, such as ionization and cause cancer to spread. Finally, background radiation. This is the amount of radiation that's all around us, and there are 4 main sources of background radiation. 2 of them are natural. So firstly, from radioactive sources. Certain rocks in the earth. The second is cosmic rays, which are just space high energy particles that interfere with the earth. The third is fallout from testing, like nuclear weapons testing. And the fourth is nuclear accidents. These are the 4 causes of background radiation and why we have radiation in our atmosphere here today. Radiation is also used in medicine to check the functions of thyroid glands, to check bones, to detect tumours and things like that. Especially, we know X-rays, that's definitely a type of radiation. And finally, fission and fusion. So in nuclear fission, the nucleus splits, and this is caused by a neutron. So, for example, we have uranium here. In fission, it's caused by a neutron being hit at it, and it then splits. This can cause a chain reaction because it not only just splits into more uranium, it also produces more neutrons, which can therefore cause a chain reaction for this one to be hit, etc., and continue. So that's nuclear fission, when a neutron collides with a radioactive source and therefore causes it to undergo fission, forming 2 smaller nuclei and 2 to 3 neutrons. Now, in nuclear fusion, what happens is 2 light nuclei, light in terms of the weight of it, then fuse together and form a heavier nucleus. And some of the mass of the nuclei can be converted into radiation. Now, we'll talk more about this in the space topic, but that's it for atomic structure and radiation. So, if you found this helpful, feel free. Now, I will return with you at 9 for English language. See you soon, and thank you for watching.